We started mostly with the basics of parametric curves and vectors. Parametric curves and vectors. It's easiest to think probably about vectors first. Got two vectors v and w. What does it mean to add them? What does it mean to multiply them by scalars? What does it mean to form linear combinations of them? AV plus BW. If A and B are positive, they rescale V and W. So maybe that's AV and this is BW. I've drawn them. So A is maybe about 1.8 and B is maybe about 1.2. So A has made V about 1.8 times longer and B has made W about 1.2 times longer. If they are negative, they go in the opposite direction. You add them via the parallelogram law, and so the linear combination like that would ultimately be a vector that looks about like this. That would be AV plus BW. So geometric interpretation of vector operations, including subtraction as well. This is V and this is W. Where is V minus W in this picture? It points either in this direction or in that direction. The way I remember it is if you add it to W, you got to get V. So it's got to point from W to V. That's V minus W. Dot product was, of course, important. If V has components A, B, C, and W has components alpha, beta, gamma, then V dot W, don't forget how to compute, is a scalar A alpha plus B beta plus C gamma. But it does also, of course, equal the magnitude of V times the magnitude of W times the cosine of the angle between them, which then allows you to find the cosine of the angle between them and therefore the angle. The angle is the inverse cosine of V dot W over the magnitude of V times the magnitude of W, which will always be an angle between 0 and pi radians, which is 0 and 180 degrees. So if you take the convention that your vector is always, you're taking the angle to be between 0 and 180 degrees, this is always what you can do. You don't have to like add pi to it or something like that. Should be able to work with, find exact values and of course approximate it. We've done things like that. Then we also thought about applying vectors to parametric curves, whether in 2 or 3 dimensions, though it's easier to draw in 2 dimensions. R of t equals x of t, y of t, z of t. It's a parametric curve in 3 dimensions. If I got rid of the third component, it would be in 2 dimensions. Parametric curve. Parametrizing, for example, lines. You got a point P and a point Q, and you want to parameterize the line from P to Q, the line segment. We talked about this with integration. Now you see why we talked about it back then. You can think of it as P plus T times Q minus P, where effectively I'm blurring the distinction between points and vectors when I write that. You could think of the points P and Q as being vectors as well, using the origin. That'd be the vector from the origin to P, and this is the vector from origin to Q. And effectively, in writing P and Q here, I'm thinking of them as being those vectors. But as far as actually computing this, you don't have to use the pointy bracket notation. You can use parentheses if you like. Though in the end, since we're calling it a vector, it's probably better to use the pointy braces. Parametrizing lines. This is the line we're talking about here. And that would be as t goes from 0 to 1. Parametrizing circles is important. Ellipses. A helix, which is a circle where you keep going up. Came up sometimes. Parametric curves. Later on, we did parametric surfaces, but you need to know parametric curves to be able to do parametric surfaces. I think it came up on exam 2 rather than exam 1, but we also got into velocity vectors, acceleration vectors, and all that kind of stuff. Velocity vector being the rate of change of the position vector, which also leads to the unit tangent vector. being the normalized velocity vector, take the velocity vector and divide by its magnitude. The magnitude can be thought of a couple different ways, can be thought of as the square root of the velocity vector dotted with itself. And in general, the magnitude of any vector is the square root of the vector dotted with itself. And we also call that the speed. And for short, I wrote that as cursive d of t sometimes. I forgot to mention cross products as well, and planes and equations of planes. Just forgot to mention those. That was more like an exam one, I think. Put it up here, cross products, planes, equations of planes. If you got an equation of a plane ax plus by plus cz equals d, a normal vector to the plane is the vector of the coefficients of x, y, and z. If you've got 3 points, you can figure out an equation for the plane because you can figure out a normal vector by taking a cross product. You got 3 points, 1, 2, 3. Find displacement vectors, take the cross product, you get a normal vector to the plane, perpendicular to the plane. That helps you figure out A, B, and C. And then you can use any one of those 3 points to figure out D. Just forgot to mention that. Back over here, we also thought about acceleration vectors as derivatives of velocity vectors, which are second derivatives of position vectors. And our main goal there was thinking about understanding acceleration vectors as well as velocity vectors in regards to the motion. Say the motion is like this. Whether you imagine that to be 2 or 3 dimensional doesn't really matter. Effectively, your position vectors, you always want to draw them starting from the origin and going out to the curve. But the velocity vector and the acceleration vector, you want to draw at the point that you're thinking about at that moment in time. Velocity vector is always tangent to the curve and has length equal to the speed. The unit tangent vector points in the same direction as the velocity vector, but its unit length. Acceleration vector, you might think, is always orthogonal to the velocity vector, but no, that's not true. It is true for uniform circular motion, but that's a very special case. Okay, the acceleration vector will point, well, in this picture, to the left and upwards here, but not to the right and downwards. It's got to point in the general direction of curvature, but it's not necessarily perpendicular to the velocity vector. It might look like this. The acceleration vector might look like that. If that's the case, if the angle between the acceleration vector and the velocity vector is acute, between 0 and 90 degrees, that's an indication that you're speeding up because the acceleration vector is kind of pulling on the velocity vector. That's a way to imagine it, at least, to make it longer. It's also making it turn because it's a curve here. And we also were interested, and by the way, for the actual motion, the acceleration vector also points in the same direction as the net force. So if you can understand acceleration vectors for a given motion, that helps you understand the force, even if the force is hard to understand in terms of thinking about gravity and normal vectors and stuff like that. You know, like if you're on a roller coaster or something, it might be difficult to think about gravity and normal vectors and any other forces that are being applied. But if you can analyze the motion and figure out the acceleration vectors, that at least gives you the direction of the force. And actually, if you know the mass, I guess the length of the force vectors as well. But we wanted to decompose the acceleration vector into tangential and normal components. There would be a unit normal vector that is perpendicular to the unit tangent vector. It was defined as the derivative of the unit tangent vector normalized, which cannot be found by taking the acceleration vector and normalizing that. It's not the same thing. N and A don't necessarily point in the same direction. This is a fundamental thing to realize. We had formulas for decomposing the acceleration vector in terms of tangential normal components, and also formulas for the curvature that were complicated. And I would put them on my note card because I don't remember them myself. I mean, the one that's easiest to remember are just the dot products. I do remember those. Tangential component is the acceleration vector dotted with the tangential unit tangent vector. Normal component is the acceleration vector dotted with the normal vector. That one's fairly easy to remember as well. The acceleration tangential component of the acceleration is the rate of change of the speed. But what's harder to remember is these three. This, you might say, well, why can't I always just use that dot product? And the problem with trying to use this one is capital N's often very much a pain to compute. We'd often very much prefer to have formulas that don't involve capital N, like these three. Of these three, I mean, certainly if you have A and AT, this one's the easiest to use. But if you don't have those things, if you don't have AT in particular, probably this middle one's easiest to use, at least if it's a three-dimensional example. So you can compute the cross product. That's the acceleration vector components. By the way, AN is always positive. That's always positive, but AT can be negative. You could be slowing down. That rate change could be negative. Then the angle between T and A would be obtuse, bigger than 90 degrees. If that were the case. Curvature had formulas as well that were complicated. There they are. How beautiful. That's for a function whose graph is in the plane, y equals f of x. There's for a parametric curve in the plane, and there's for a curve in three-dimensional space. Beautiful to look at, maybe not so much fun to use, but should be able to use them. On exam 2, there was an example. It's a two-dimensional example that we did. I don't remember if it was 1 or 3 that was used. Maybe you could use either one. I mean, that's for got a cross product in there, so you probably can't do that. I think it must have been this one that we used. Curvature tells you how curvy the curve is near the point. If the curvature is large, it's a very tight curvature, very curvy. A very small radius of curvature. The radius is 1 over kappa. So if kappa is large, 1 over kappa is small, the radius is small. It's like a small circle near that point. If the curvature is small, it's almost straight. Small kappa, 1 over kappa would be then large. It's like a part of a large circle. The radius of curvature is large. R is 1 over kappa. After that, we sort of got into what you might call the main part of the course. Multivariable functions. Most commonly, z equals f of xy. Though we could also consider u equals f of x, y, z. We talked about graphs, both surfaces above some domain in three-dimensional space. Also the contour maps of level curves, which might look like this. That might indicate a mountain or a valley. And you could also have saddle points where the level curves might look more like this near a point. A mountain or valley there and a saddle point there. Those were curves in the xy plane on which the function was constant. Easiest, if your function is linear, then your level curves are straight lines. And the three-dimensional graph is a plane slanted in some way. Harder if it's nonlinear. Limits. Oh, limits was always really tricky because weird things could happen. Well, we did have some basic kinds of problems that we thought about. It came up on exam 2 or 3, one of those 2 exams. Partial derivatives. Oh, There was that really long partial derivative problem that took a whole page on one of those exams. If I have partial derivatives and second order partials to compute on the final, it would not take an entire page. Okay, I'll give you one that will not be quite as nasty. You're welcome. Okay. Why did I do it on that exam? It's an important example I wasn't thinking about. Some of you actually tried to do it with a limit. I didn't realize people would do that. So I thought it would be better than it was. I mean, I was trying to give you hints actually in class too about how to make it easier, but it was still a pain. You actually did better than I expected on it, but there were directional derivatives, gradient vectors, and directional derivatives. Gradient vector of such a function like this would be a two-dimensional vector of partial derivatives. And a directional derivative of a function at a point is the gradient vector of the function at the point dotted with whatever unit vector you happen to be looking in the direction of. U must be a unit vector. And so if the problem is described without a unit vector to begin with, say, hey, we're at this point, we're trying to find the directional derivative in the direction going from this point to this point, then you got to find the displacement vector, which may not be a unit vector, and normalize it first, make it unit length by dividing it by its length before you use this formula. By the geometric interpretation of dot products, and since unit vectors have unit length, that's the same as the length of the gradient vector times the cosine of the angle between the gradient vector and the unit vector. Now, the gradient vector might be kind of long and the unit vector could be short and not necessarily the same direction. This angle could be non-zero. When the angle is zero, cosine of zero is 1, as big as possible. So this directional derivative is big as possible. It's maximized in the direction of the gradient vector. If u and the gradient are in the same direction, that's when this is maximized. And its value is the actual magnitude of the gradient vector. And it's minimized if the angle is 180 degrees. If u is pointing in the opposite direction of the gradient vector. And the minimum values when the cosine of theta is -1, the minimum directional derivative is the opposite in value of the magnitude of the gradient vector. When you draw gradient vectors on top of level curves, they're orthogonal to the level curves and pointing in the direction in which the function is increasing fastest. Here, I guess I'm drawing them going away from that point in the middle there. So that point must be a minimum because the gradient vectors are pointing in the direction in which the function increases. We also had miscellaneous topics, including the chain rule, local linearization, essentially linear approximation with tangent planes. And then the application was to extreme values. We got the local extreme conditions, where you take the partial derivative, set them equal to 0, solve for the critical points. Test whether they're max, min, or saddle points by computing the second order partials. And there's the discriminant thing, which is actually a determinant of a matrix of second order partials. And if it was negative, then the point was a saddle point. If it was a positive, then it was either a max or a min, depending on whether the graph was concave up or concave down near the point. And then the global was when we were optimizing, for example, over, I don't know, like an ellipse or something. And we either, well, you find critical points in the interior, and you also think about what's going on in the boundary with one of two methods, either by plugging in a parameterization of the boundary into the function, or by using the Lagrange multipliers. Either or, you should be able to do both. I think on the exam, I had to do both even. In two different problems. Then we got into integrals, double, triple, Quadruple, no, we stopped at triple. Applications, center of mass. Center of mass. What else? We talked a little bit about applications of probability, but probably not enough to put that on the exam. Then more general kinds of integrals. Well, change of variables, which included polar coordinates, cylindrical, and spherical. I did not ask you a spherical coordinate question. Spherical on your midterms, so I guess I should not for the final, but it is important for your future if you take lots of physics. And then the general one involving the Jacobian matrix and the Jacobian determinant and its absolute value. There is a sample problem from the 2018 exam and also Dr. Yang's exam on the general one. And then all the stuff with surfaces, well, okay. Line integrals, curl div, fundamental theorem of line integrals, FTLI, fundamental theorem of line integrals. If you've got a conservative vector field, it's the gradient of some function. You can do the line integral by finding the potential function. This came up on the last exam and doing a difference, just like a regular integral. It's simpler. And then the surface integrals. And then, well, there's Green's theorem, divergence theorem, and Stokes's theorem. I will not put Stokes's theorem on the exam, I think. Green's theorem and the divergence theorem could be. The Green's theorem came up in the last exam. Divergence theorem could come up on this one. Dr. Yang's example, I sent you a note about, involved the calculation that it's technically doable by hand, but it took me like 20 minutes. So, and it's very easy to make a mistake. So probably he wanted them to use the divergence theorem on it actually as a shortcut, but he didn't say that. I mentioned this in my message. I have started working on a problem that involves the divergence theorem. And I'm not finished with it yet, and I'm not remembering exactly how I phrase things yet. So I might give you some more hints about that. I will not do Stokes's theorem. It's a bit too much, I think. I would suggest, for one more bit of insight, reading the last couple pages of section 14.7, when they talk about how fundamental theorem of calculus, fundamental theorem of line integrals, Green's theorem, divergence theorem, and Stokes' theorem are all kind of similar to each other in a certain way. It's kind of a little weird, but true. And in fact, you can combine them all in one theorem, a bigger, broader, more general version called the general Stokes's theorem that I studied once as well. And it was, yeah, I don't really remember it very well. But if you took grad school stuff on this, you might learn about that more general Stokes's theorem. Okay. They all fall under that umbrella. They're all essentially the same theorem in different forms. The real life interpretations, good for your future. I'm not going to test you on them of divergence and curl and stuff like that.